the intermolecular forces depends on the types of the particles that we're talking about. And the state of matter at a given temperature reflects the strength of those forces. So if we see that that Velcro holding them together is very strong, we're going to have to get to a much higher temperature before it can melt, and a higher temperature for it to boil. If those forces are very weak, maybe the Velcro's old and worn out, then it will melt at a lower temperature. The particles don't need to have as much movement to break away from each other. These intermolecular forces come about because of charges. Permanent charges, partial charges, and temporary charges on the particles. So here's Coulomb's law again. The energy, the potential energy of two oppositely charged particles, Q1 and Q2, is dependent on R, 1 over R. So it decreases with increasing magnitude of charge and decreasing separation. Delta E is going to be, E is going to be negative, because one of these is negative and one's positive. Remember, a negative potential energy is a good thing. That's low, and it's trying to get low. And so the potential energy is going to decrease, become more negative, when we increase these charges. If we go from +1 and -1 to +2 and -2, this will go from a product of 1 up here to 4. So it will be 4 times as large in magnitude. And decreasing the separation will cause this to become larger in magnitude. So the force of attraction is greater when objects are close and when the charges are greater. And this is very similar to magnetic forces. You stick a magnet on the refrigerator, it's great. You put a piece of paper and you put a magnet on the paper and it sticks. And then you add another piece of paper and another piece of paper. And depending on how strong the magnet is, 2 or 3 pieces of paper might be enough distance that that magnet won't stick anymore. Right? You're trying to hold up that notice from school and it keeps sliding down because the paper's too thick and your magnet's not strong enough. Little bit of distance makes a big difference in these forces of attraction. So bonding forces we have been talking about. Bonding forces are within the molecule. So here in water, between the oxygen and the hydrogen, we have a distance of 96 picometers. These intermolecular forces are much weaker because the distances are larger. Here, 300 picometers versus 96 picometers. So because they're farther apart, they're much, much weaker than actual covalent or ionic bonds. So what are these forces? Well, the first one is called the dispersion force. And this has a few other names. Dispersion force is not my favorite name for it. They're also called London forces or London dispersion forces. Oh yeah, I've actually got that part right here. They're also called van der Waals forces. This is not the same as dipole-dipole. And none of those are my favorite name, which is not, Steve or something. Induced dipoles. That's my favorite name for them. I think it's more descriptive, except I can't spell it. Induced dipole forces. So all of those, same thing. All molecules and atoms have dispersion forces, and these are a result of fluctuations in electron distribution. So here's an illustration of, what is that? That must be helium. 2 electrons, right? And so if we look at any given instant, chances are pretty good that those electrons are going to be spread out in that orbital they're occupying, right? But occasionally, they could both end up on the same side. So here we have protons in the nucleus. There's a positive charge here. And now we have both of our negative charges on the same side of the nucleus. That makes, overall, this atom have a dipole. It's a little negative on this side, and it's a little bit positive on that side. So at any given instant, you can have these electrons be unevenly distributed. And this happened to my children. I think children are a lot like electrons. They're kind of unpredictable, and they start out small at least, and they get big after a while, but they start out really small. So these small, unpredictable beings around your house, right? 6 kids, usually they're spread out all over the place. One day, I walk in the living room, all 6 of them on half of the couch. What? I can't remember what they were doing over there, but I took a picture because that just never happens. But if kids could do it, electrons could do it too. So these electrons, normally they're spread around, but they're just doing their own thing. They could all be on the same side, and it happens. And so that's a temporary dipole. We get an instantaneous or temporary dipole. And when that happens in one, it induces a dipole in the other. Because now this atom has a partial negative charge here, that's a lowercase Greek delta, and a partial positive. And this partial positive of this small atom is attractive to the electrons over here. They're like, oh, look, right? It's a little bit like going on one of those blue and white cruises around the San Francisco Bay. And most of the time the people are all spread out, and you go around Alcatraz. Oh, hey, did you see? And everybody goes to one side of the boat, right? And then it tips just a tiny bit. It lists. So this one was listing, and it induced the next one to list. So this one, these electrons were attracted to this positive here. Well, now we have negative and positive. There's an attraction there. This one's lopsided. It induces a dipole in this one, and there's another force of attraction in here. This force of attraction is called the dipole force. It's between 2 instantaneous dipoles in neighboring atoms or molecules. So we've got this instantaneous dipole. It comes and it goes. How long did the kids stay on the couch? Probably about 30 seconds, right? And that was it. Probably never ever happen again. So this dipole happened by chance. It induced dipoles in neighboring atoms. Then this goes away, and then they're like, aw, and that one goes away, and this one goes away. And so this dispersion force comes and goes and comes and goes, and it's very, very weak, but it is significant. The magnitude of the force depends on how easily those electrons can be polarized, how easily this atom can get lopsided in its electron distribution. So if we look at the series of noble gases, helium through xenon, here's the molar mass and also the illustration telling us that these are getting bigger and bigger and bigger, right? Xenon is much larger than helium. Helium has 2 electrons. That makes me think of a mom that has 2 kids, and she's got one by this hand and one by this hand, and they're going to the fair, and she knows where those kids are. And they're not going to both get on one side and maybe get away from her. And xenon has 54 electrons, and xenon goes to the fair. We don't go to the fair because it's a great place to lose children and money. So we just don't go anymore. But here's xenon going to the fair with 54 children. She should have had her head examined in the first place for having 54 children, but then for taking them to the fair, she probably should be committed. She wanted to maybe lose them or something, I don't know, but you can imagine trying to corral 54 children by yourself. They're going to get lopsided, right? They're going to just, Ferris wheel, and off they go, right? Larger molecule, it's easier for that electron cloud to get shifted. So it will form probably more frequently, the instantaneous dipoles, and when they form, they'll be larger. And so we see a larger dispersion force in the larger molecule. And we see this reflected in the boiling points. Helium boils at 4 Kelvin, and xenon at 165 Kelvin. Higher boiling point indicates higher strength of intermolecular force. Those xenon atoms have to get up more thermal energy, more kinetic energy before they can break loose from the dispersion forces. So the dispersion force generally increases with molar mass. And shape can also play a part. Here are two isomers of pentane. Normal pentane, which is just a straight chain of carbons, and neopentane, where this carbon has 4 other carbons attached to it. So this is going to have more of a spherical shape to it, and this is going to be more of a linear shape. These two molecules have more area over which they can interact. If you think about something this shape that was covered in Velcro and another one like this, these could stick together pretty well. They've got all this surface area here. These are basically like 2 balls, and they're only going to stick at this one little point. The amount of stick-togetherness between these two is less than those. Does that make sense? Molecules that are long and spread out will have higher, stronger intermolecular forces. So shape is important. Molar mass is probably the easiest thing to predict when you're comparing similar elements or compounds. You can't compare like normal pentane to, water or sodium chloride or something and just go based on mass, because those are completely different kinds of compounds. The second force is called the dipole-dipole force, and this is present in all polar molecules. So the first one was present in all molecules, and this one, dipole-dipole force, in all polar molecules. Polar molecules have permanent dipoles. So here we have, what is that? That's ether, I think. Dimethyl ether. Anyway, it kind of looks like a sideways octopus or something. But there's an oxygen here, and this is the negative end, and this is the positive end. It's a polar molecule. It always has a dipole. So the idea of this interaction between partial charges is the same, but this interaction is always there. It doesn't come and go. And so this is going to be a stronger force because of it always being present. The polar molecules have dipole-dipole forces in addition to the dispersion forces. And when we compare the polar with the nonpolar, we see differences in melting and boiling points. Here's formaldehyde and ethane. And if we look at their formulas, we see this one has an oxygen in it. The oxygen is bonded to carbon. There's no hydrogen bonding or anything here. Wait, because I haven't told you about that. Forget I said that. Here's ethane. This one is nonpolar, and this one is polar. Molar mass, almost identical. But look at the boiling points. Minus 19, minus 88. Melting points, minus 92, minus 172. Big difference here. It doesn't have anything to do with differences in dispersion forces because they have the same mass. But this is polar and this is nonpolar. The higher melting and boiling points are because these molecules stick together more strongly than the nonpolar molecules do. Polarity is important in determining miscibility. Miscibility is kind of a funny word that chemists use. This isn't a real word, but mixability. Will the two liquids mix? We use this little phrase, like dissolves like. Here we have oil and water. Water is polar and oil is nonpolar. The oil only has dispersion forces. The water has dispersion forces and dipole-dipole forces. These forces of attraction are much greater, and so it excludes the oil. It just squeezes it out. It can't get in. So which of these molecules have dipole-dipole forces? How do we decide if something has dipole-dipole forces? We see if it's polar. So Ci4, I wrote the name because it looks a lot like Cl4, which doesn't exist. Carbon tetraiodide would look something like this. I'm going to ignore lone pairs on terminal atoms. Is that molecule polar or nonpolar? Nonpolar. Does it have dipole-dipole forces? No. Only polar molecules can have dipole-dipole forces. How about this guy? Polar or nonpolar? Polar. Does it have dipole-dipole forces? Yes. How about HCl? Is that polar? We can't look at the central atom. It's diatomic. There's only one bond. If the bond is polar, the molecule's polar. Is the bond polar? Yeah. So this also has dipole-dipole forces.
To determine whether that molecule is polar, is that the difference of electronegativity then between
yes.
hydrogen and...
Between hydrogen and chlorine.
Okay.
So here's hydrogen, there's an illustration of this bond. Because there's only two atoms, if the bond is polar, the molecule is polar. And so the best way to determine it is to look up the electronegativity values of hydrogen and of chlorine and see how different they are. For the purposes of questions like this, we can just go with, well, are they the same? If they're the same, it's nonpolar. If it's the same molecule, like if we had H, is that bond going to be polar?
No.
It's going to be nonpolar, right? If they're different, chances are very good it will be polar. So you don't have to whip out a table of electronegativities. But you identify the polarity of the molecule, and that tells you what kind of forces it has. Any questions? The third type is called hydrogen bonding. This is like super dipole-dipole forces. You put a cape on them, Superman. The name is a little misleading. Hydrogen bonding makes us think of covalent bonds or ionic bonds, and that's not what this is. It is just an electrostatic attraction between dipoles in neighboring molecules. But when we have a polar molecule containing hydrogen bonded to fluorine, oxygen, or nitrogen, those are the three most electronegative elements, and they're also small. Then we have extra strong dipole-dipole forces. So it's pull out the pen first. Okay, I did it again. I need my head examined. So what did E.T. keep saying? E.T. phone home. Phone home. I loved that movie. F-O-N bonded to H. That's what you need for hydrogen bonding. You have to have the H bonded to one of these, nitrogen, oxygen, or fluorine, and it has to be a polar molecule. But chances are good if that combination's in there, it's going to be a polar molecule. So hydrogen bonding, stronger than dipole-dipole forces because the charges are different. So here we have, I think this is hydrogen fluoride or some similar thing, probably hydrogen fluoride. So the hydrogen end is partially positive, the fluoride end is partially negative. The partial charge here is larger than on a regular polar molecule. And because of that higher charge, the force of attraction is greater. Here we can look at hydrogen bonding in ethanol. Ethanol has this OH group, at the end, 2 carbons with their hydrogens, and then oxygen and hydrogen. We've got that OH bond, polar molecule. And so we get this attraction, the hydrogen bonding between the hydrogen of one molecule and the oxygen of another molecule. It is between molecules. Here's hydrogen bonding in water. This oxygen can be hydrogen bonded, attracted to the hydrogen on this molecule and also to the hydrogen on another molecule, because water is a very small molecule. On the ethanol, the carbon part kind of gets in the way of having multiple hydrogen bonds forming, but in water there can be multiple hydrogen bonds. Hydrogen bonds between molecules, chemical bonds between atoms within a single molecule. The hydrogen bonds are 2 to 5% as strong as a covalent bond. So they're much, much weaker. I mean, they're the Superman of the intermolecular forces, but they're still very weak compared to actual covalent bonds. If we compare ethanol and dimethyl ether, these are isomers of each other. They have the same molecular formulas, just have their atoms arranged differently. So they have the same molar mass. Do these molecules have dispersion forces? Yes, because all molecules have dispersion forces. Based on their size, their dispersion forces should be the same strength, right? Are these molecules polar? Well, let's do this one first. Is ethanol polar? Does it look lopsided, like one end is different than the other end? Yeah. We've got an oxygen way over on the end here. This one might be a little harder to think about. So let's look at the Lewis structure for that. What's going to be the geometry around the oxygen? It's going to be bent because of these lone pairs. So this group is actually more over here, and it's bent. And so then you've got the oxygen on one end, and you've got the carbons and the hydrogens on the other end. Carbon and hydrogen are not next to each other on the periodic table, but they are close enough in electronegativity that a carbon-hydrogen bond is considered to be a nonpolar bond. So this guy is polar. So this one's polar. Is this capable of hydrogen bonding? It's got hydrogens on it, and it's got an oxygen. But the hydrogen is not directly bonded to the oxygen. So this one has dipole-dipole forces. Ethanol also has dipole-dipole forces, but ethanol has hydrogen bonding because we've got oxygen, hydrogen here. And when we look at the melting and boiling points, ethanol boils at 78 degrees, dimethyl ether boils at minus 22 degrees. There's a huge difference. And that tells us there's a large difference in the strength of the intermolecular forces. Any questions? Stronger intermolecular forces, higher melting points, and higher boiling points. I love this graph. So this is a graph of boiling point versus molar mass. And we're comparing compounds between hydrogen and group 4A and group 6A elements. So here's group 6A. There's carbon with 4 hydrogens, silicon, germanium, I almost said geranium, and tin. So they form tetrahydrides. And there's a trend here, right? It's not exactly a straight line, but it's pretty good. And then we look at the group 4A. And if we start up at this end, here's tellurium and selenium and sulfur, and then oxygen should be down here, shouldn't it? If we were to draw a line on that graph, we would expect it to be down there somewhere. But it isn't. It's way up here. Water has hydrogen bonding. None of the rest of these do. these molecules are nonpolar. These molecules are all polar, and their boiling points reflect that. They're higher. And we see this trend going up as molar mass increases because dispersion forces get stronger. But water just blows all those trends out of the water because of hydrogen bonding. Sorry, I just could not resist. So which has the higher boiling point, HF or HCl, and why? HF, because it can hydrogen bond. So both of these molecules are polar. They're diatomic molecules, hydrogen fluorine, hydrogen chlorine. The difference is HF has an HF bond, hydrogen fluorine bond, and so it can hydrogen bond. Now HCl is going to be a little larger, right? Because chlorine has a molar mass of 35 and fluorine has a mass of 19. But difference in size, they do affect the dispersion forces, but the dispersion forces are so weak that you throw something in like this, hydrogen bonding, and that beats all the others. So the hydrogen bonding wins. So we say that, hydrogen bonding. Yeah, do you remember the cartoon that was up here on Tuesday? Yeah. The name's Bond, hydrogen bond. Somebody erased it. I'm so disappointed. I have a picture of it. There's a fourth. No, it isn't. There's something else. Perspective drawings of geometries now. There's another one called an ion dipole force. This does not happen in a pure substance. It only happens in mixtures. When you have an ionic compound mixed with a polar compound. And as the name suggests, it's an interaction between an actual ion, which has a full positive or negative charge, and a dipole of a polar molecule. These are really important in aqueous solutions of ionic compounds. And since they are an interaction between molecules, technically they are an intermolecular force. In 3A, we don't tell those students about these forces. But it's the ion dipole force. It is stronger than hydrogen bonding even. So this is what happens when sodium and chloride dissolve in water. The sodium ion has a positive charge, and all the negative ends of water molecules are attracted to it. Chloride has a negative charge, and the positive ends of the water are attracted to it. So, water is kind of like this two-faced molecule. It can be friendly with the negatives, and it can also be friendly with the positives. So this graph just summarizes these four intermolecular forces, their names, where they're found, gives you a picture, and then the strength. You definitely need to know this table. It's a good table. Hydrogen bonding is really important. Hydrogen bonding is what holds the two strands of your DNA together and what allows your cells to replicate. Because when DNA replicates, the two strands are separated and a new strand is formed on each of the existing strands. These are the bases on the DNA strand. Thymine and adenine, they will hydrogen bond in two places. Cytosine and guanine can form 3 hydrogen bonds. And so these act like a lock and key, almost two pieces of a puzzle that fit together, so that this one strand of DNA can be replicated. The other strand is complementary. Where there's an A on this strand, there's a T on that strand. Where there's a C on this one, there's a G on this one. And so we can take these two strands apart, which were also complementary, and you make a new complementary strand for each of them, and you end up with 2 copies of the original strand. Very, very cool, and all made possible by hydrogen bonding.